Let's look at an example. Let's see how this works. This is a fairly simple example. In fact, we know exactly what is the solution of this differential equation. So we're going to use this example also to see how the method works and see how we can extract information from the solution we obtain. Right? So first of all, we're going to have to write the differential equation in the proper form. Remember, the one key requirement, the only requirement of the method, is that we must be able to isolate y prime. Of course, that's very easy in this situation. Next, what we're going to do is we're going to construct the iterative formula. Remember, in order to construct the iterative formula, we're going to say that yn plus 1, the next y coordinate, is going to be equal to the previous y coordinate plus the value of the function at the previous point times h. But in this case, the function of xn, yn that we're looking for, remember, what is it? It is the slope formula. So it's just 2y. And so we're only going to estimate it at yn. Notice that in this case, the slope does not depend on x, depends only on y, and that's fine, that's great. So it simplifies our calculations. Again, in most of the examples and test questions that you will have, this formula will end up being pretty simple to work out anyway. We can even work this one out a little bit more simply, do a little bit of algebra, factor the common yn, and come up with that. The next issue is, well, what are we going to use for h? The choice is ours. Okay, as I said, the smaller it is, the better it is. But then, of course, if we take a small h, if we want to go to any distance away from our initial value, we have to do several iterations. Just for the sake of illustration, let's say that h is going to be equal to 0.2. Okay, so what does that mean? It means that first of all that our formula simplifies to yn plus 1 is going to be approximately equal to 1.4 times 1 times yn. Okay, so let's start the process. Okay, so we have our recursive formula, and we're going to use that formula over and over again. We're going to start from our starting point, which was 0, 1, which means that x is equal to 0, the first point, and y is equal to 1. Now we're going to put the y value, that's the only one we need, into our recursive formula, and that tells us that for the next point, which is 0.2, why is it 0.2? Well, remember, because we chose h to be 0.2, and we're moving by 0.2 each time. So we started from 0. With x, we're going to go to 0.2, put the 0.2 into the formula. Actually, we don't even need to put the 0.2 in the formula. We just need to write it down for the x coordinate. So for the y value, we're going to end up with 1.4. Yes, I know I could have written it as 1.4, but I'm reminding you that that comes from a potentially more complicated formula, times 1, which is the previous value of y. Simple calculation, we'd end up with 1.4. That's the y coordinate of the second point. Okay, off to the next one. x2, again, we're moving up by 0.2 more, so we're at 0.4. Apply the formula again. Feel free to pause to check the calculations at each stage. We end up with this new value, which is the new y value. Keep going, 0.2 further away, new y value, new y coordinate. And then we keep going. We'll do just a couple more. And so this is what you end up with. You want to check with your calculator. Oh, if you check with your calculator, by the way, you may find out, and probably you've already figured it out, that I'm also rounding the numbers that I'm obtaining at the end. They definitely have more than just 2 decimal digits. Okay, but again, that is okay because we are doing approximation, so it's not too bad. But if you have a chance of using more exact values, more decimal digits, that's a good idea. Just one more. Okay, so the last one, we're going all the way from 0 to 1. It gives us 5.38. All right, so we have a table of values. Let's see what we can do with this table of values. Well, what we can do with this table of values, of course, is to use it to plot some points and see what the shape of this solution is. So, first of all, we're going to plot the first point, the point 0, 1, and then the second one, and then the third one, and a few more. And then if we have patience, or if we're using a computer or a calculator, we can compute a few more. Okay, so let's say that this is what we get after a few iterations of the formula. Okay. Now, what can we do with that? We can interpolate it. What does that mean? Well, if these are the points that we computed, then probably the solution is going to be looking something like that, right? We're just simply going to join the dots, as you did way back in junior high, probably. Okay. Now the next thing we can do is we can analyze this shape. Let's see, what can we say about this shape? First of all, we can see that from 0 to 1 it's pretty flat, and then it starts curving more and more as we go towards 2. Oh, we're not surprised, because if you remember, the solution of that thing is exponential. Okay, but again, let's pretend we didn't know that. And so that's one thing that we can observe. We also observe that it looks like the concavity for this curve is up, which means that each of the tangent lines that we're building as we're constructing this approximation is going to be below the actual curve. So what that means is that this approximation we're getting is going to be an underestimate. So all the estimates we're doing, they're along the tangent line. The tangent line is going to be below the curve, so they're all underestimates. Okay? Now, what we can do is, if we actually have a chance of getting the exact solution like we do in this case, we can compare it to the solution. And here is the solution. Of course, solution is y equals e to the 2x. And yes, as we said, the concavity is up, and what we're getting is an underestimate. And notice that between 0 and 1, where the curve was pretty flat, we get a very good estimate, right? But beyond 1, once the curvature starts getting bigger, our estimate is not very good anymore. Okay, so this is a method that, with this choice of the h of 0.2, we can only take it maybe from 0 to 1, or a little bit more than 1. If we need to go beyond 1, probably we need a smaller value of h.